Hello, welcome everybody. Brilliant. So my name is Claudia, I'm your session chair, and I just wanted to, first of all, welcome you here, but also tell you a bit about how we're going to run things. So everybody's going to do 10 push-ups and then no. So what will happen is after our first speaker, Sandra, finishes her talk and we finish the questions as well, we are all going to exit this room and then come back in if we're interested in the second presentation. The reason being that we need to get our badges scanned and so on at the entrance. I think only I get to stay in the room together with Jake and our other AV people. So without further ado, I'd like to introduce Sandra Johnson from Pegasus. She's going to talk to us about trust in a trustless environment. Thank you, Sandra.
Hi everyone and welcome. I must say I was really happy to see the setup here in the room being quite friendly, you know, not just me talking to a row of people. So today I want to talk to you about trust in a trustless environment. And what I want to do is unpack that a bit, but what they've asked us to do is give a bit of a bio before we get started. Now, because I'm a bit of a dinosaur, there's probably more so than with other people. So I basically studied at KwaZulu-Natal in South Africa, where I did an undergraduate in mathematics and statistics, and also then worked there for as a temporary part-time lecturer. I don't think you can get more sort of part-time than that, in statistics. Then I decided I either have to carry on studying in statistics because you just get boring work, or you go and change career. So I got interested in IT, and IBM employed me as a trainee programmer, and then I progressed and stayed with them for quite a long time. And then my husband's British, and we ended up moving to the UK for a few years, and I went contracting. And the reason I'm telling you this story is I was sort of heavily pregnant at that stage, and FI Group was started by Dame Stephanie Shirley. And has anyone heard of Dame Stephanie Shirley? I know that you have. Please have a look at her. She went by the name of Steve often because she started freelance programmers way back when it was you needed your husband's signature to open a bank account. And she revolutionized really IT, women in IT, in my opinion. And I doubt if I was trying to get contracting work for anyone else, if they saw someone highly pregnant, I got a job for 3 months. It was probably one of the most productive contracts that I ever did. And she's really quite inspirational. There's a TED talk that she does. And then I worked at some of the other places that FI Group. So she started off as freelance programmers, then it was F International. And then I had a midlife crisis. I decided I really miss statistics. I think I want to study a bit more. And I had another fantastic, inspirational woman in my life called Distinguished Professor Kerry Mengerson from QUT. And I studied under her. She was my supervisor for my PhD in statistics, environmental statistics. So, and then I also did a bit of research with QUT, then decided, well, I'll go back into industry and worked as a data scientist at Flight Centre, and currently I then also got interested in blockchain, so now I'm working with Pegasus Consensus. So as you can see, my career path sort of goes all over the show. But it just shows you in tech, I think it gives us fantastic opportunities. It's flexible, you know, it worked in with a family. For me, it meant you don't have to choose a career between a family or a career. It really is something that's more flexible than most. So let's have a look a bit at trust in a trustless environment. So first of all, we'll have a little bit of a look about what do we mean by trust. And then this is a tech conference, so I'm going to look a bit at blockchain. So first of all, trust. What do you say, what would be your definition of trust? If I say trust, what do anyone, what does that conjure up in your mind? Yeah, reliability. So if we go to the Oxford English Dictionary, how they define it is a firm belief in the reliability, truth, or ability of someone or something. So now if we talk about a trustless environment, what does that mean? Well, I thought about it and I thought trustless either means you cannot trust, or perhaps it means that you don't need to trust. If we look again at the dictionary's definition, it talks about untrustworthy, deceitful, distrusting, way, suspicious. But really, within a blockchain perspective of it, it's really the fact that we don't need to trust. So let's look at it from a bit of a blockchain perspective. Now, what blockchain is doing, in my opinion, is really being a lot more transparent, which engenders trust. So you normally, well, not normally, but often solutions in IT would have been, you get some data, it goes into this magical little black box, it does some magic, and out comes something. And you don't really see what's going on in that little black box. So that is why you'll find that in the blockchain community, so much of it is open source. So anyone can see what's going on. It engenders trust even around the developers. People can contribute and develop the whole technology. Now, I don't normally quote Ronald Reagan, but he said, trust, but verify. And I think that is also something we do within the blockchain environment, is yes, we can trust the whole ecosystem, but we need to also verify that it is in fact trustworthy. And this quote here, I think, describes it quite succinctly. The blockchain does one thing. It replaces third-party trust with mathematical proof that something happened. Now, as with anything in IT, it's littered with a bit of jargon. So some of the terms you might get, that you might hear are things like block proposer, a validator, consensus, distributed ledger, decentralized, a fork, miners, node, permissioned, permissionless, private, and public. So I'm not going to touch on all of those, really, because well, first of all, we won't have time, but I will try and draw attention to them as I go through that. So what do we mean, first of all, by distributed versus decentralized, or both of them? Because really, in a blockchain, it is decentralized and distributed. So distributed really is centralized is, as you can see in the middle, it goes through a single point. So, and that is the whole concept that we're trying to get rid of, is this control that is in one single place. So if that gets compromised, everything is compromised. So you can see in the decentralized one, you've got different, it's spread around there. And distributed is more about like the location. So you might have the computers, or you have a copy of things in different locations. So now let's have a quick look. It's going to be a high-level, quick whirlwind tour of blockchain. So we're just going to look at why blockchain, what is blockchain, how does it work, and what are the types of blockchain. So why blockchain? Well, if we go back to Satoshi Nakamoto, he did the white paper on Bitcoin, and it talks there about digital signatures provide part of the solution, but the main benefits are lost if a trusted third party is still required to prevent double spending. So the whole idea is that we want to get away from this centralized third party, this trusted third party. And there's a lot of questions about Satoshi. Is he one person? Is it many persons? And really what I want to get across as well is that blockchain isn't Bitcoin. Blockchain technology is the underlying technology that powers these cryptocurrencies, and there are a lot of them. So what is blockchain? So if you can think of a ledger, everyone familiar with a ledger type system? Because my husband said, I don't know what a ledger is. But in the paper-based form, if you have entries in there, you don't sort of rub something out and then add something else in. You would add on, if something happens, you'll add another entry into your ledger. Sorry, I'm pressing the wrong button. So what happened is initially the paper-based ones would be transformed and digitized and put onto a central database. But in the event of blockchain, what is happening is that ledger is really written onto a blockchain, which is then present in a distributed network. So a copy of that ledger is not held in one place, it's on each of those computers that you can see in that environment. So it records and tracks not only these financial like ledger type entries, but really anything of value. So say, for example, ownership of land, or it's used a lot in supply chains, you know, can I track where things have been when, and that type of thing. So it's not just about currencies. So if we just look at how does a blockchain really work, this is now very high level, I'm not going to go into detail, but really it's, you've got transactions that go into a block, and these blocks are connected in a link to each other in a chronological way. So as I mentioned before, is that if I want to go and change one of the transactions or something in that block, and then saying, oh no, so-and-so doesn't own it anymore, it's now mine, I can't just go and update that block. What I do is another block which changes the status quo, saying I now have this much, will be added on at the end of the blockchain. So it really is a way that it records changes over time while it keeps the historical information. And these blocks are really are produced at regular intervals, and basically there's a way in which people can adjust the frequency by making it harder to solve the cryptographic puzzles, which I'll come to in a minute, and they can adjust their difficulty if they want to perhaps increase the rate, the sort of how long it takes to create another block. And now with processing time, we look at some of the key, the two main ones I'm going to mention is Ethereum, because that's what our company are working on. So we're creating a Java client for Ethereum. And in Bitcoin, the average number of transactions per second is 39. In Ethereum, it's 109. And Bitcoin, it takes on average about 9 minutes. So I took this, I wrote all this down on the 26th of July, so it's pretty current. And Ethereum, the average block time is 13.5 seconds. And people tend to compare that to say, oh yeah, but Visa can do, and what I got off from the Visa website is they claim they've got capacity of 65,000 messages, sort of transactions per second. But that's not true, really. That might be capacity, but what is actually happening, when I looked it up, it's 1,700 per second. So it's still really fast. But what I'm trying to say is that people claim these things, and then everyone mentions it, and 24,000 was mentioned in an article somewhere. Now everyone says, oh yes, Visa can do 24,000 transactions per second, but that's not reality. It might be able to do that, but it's certainly not doing it currently. So basically what happens in a blockchain is transactions are selected from a transaction pool, and in that transaction pool people say, well, I'm prepared to pay this much to get my transaction included and mined by the miners. And basically a cryptographic puzzle has got to be solved to create a block on that blockchain. And once it is solved, a miner might say, I've got the solution, and then they broadcast that to everyone on the network. And thereafter, the network participants can then verify it. So the concept here is it's really, really hard to solve this cryptographic puzzle, but it's easy to verify. And when that's been done, then the block is added to the blockchain. Now, in Ethereum, the blockchain size currently is 285 gigabytes. So if you want to download all of Ethereum, if you've got that amount on your laptop, on your computer, you can download it and you can run a full node. And what you'll need to do is install, and I'm using Ethereum because, as I said, Pegasus, who I work for, runs an Ethereum client, and Pantheon is the client, the Ethereum client we're developing, and my wonderful colleagues at the back there are busily coding up this client. And the idea with Pantheon is that it's a Java-based client. So what we're trying to do is bring down that barrier to entry into blockchain. So by a lot of enterprises would already have quite a big community of Java developers and also, say, database developers. But if we can expose that blockchain technology to them through a medium that they're familiar with, a language they're comfortable with, without having to learn yet another one, because on Ethereum they write what's called smart contracts in another language called Solidity. So there's another barrier for entry. You've now got to learn yet another programming language. But if all that is automatically generated for you by just Java calls, then that makes life a lot simpler. Now, as I mentioned before, the miners, and I think it's quite aptly named miner, and if you want to become a miner, you will have to install some additional software called, in Ethereum, it's called ETH Miner. And typically people will join a pool of miners because, as I mentioned before, it is a lot of energy and power goes into solving this cryptographic puzzle. So you group the transactions into blocks, you solve this puzzle, which is typically, we'll say, you have to try and find a number in a certain range. And then the first person to solve it, broadcast it, and then if you are the winner, you get, in Bitcoin, 12.5 Bitcoins. Now, the interesting thing to note, in Bitcoin, there's only a limited supply of Bitcoins, and I can't remember exactly how much it is. Can you remember? I think it's like 21 million, or I don't know. And in Ethereum, a miner receives 3 Ether as a reward for saying you've solved this cryptographic puzzle. And then the miners will agree that the block is valid and can be added to the pool. Now, this concept of doing that work to solve the puzzle, that is a mode of consensus we call proof of work. So it's really proving you've done that work. But it takes a heck of a lot of electricity, and that's what I try to show here, is these banks and banks of computers. And someone mentioned the other night that apparently Iceland and China are the 2 big places where they can have these big sort of farms, mining farms, because of cost of electricity. And then I said, well, why Iceland? And I think not only is there big hydroelectric, but also the cooler temperatures, because a lot of energy is used as well in cooling these computers. So my colleague was saying that is also another factor to take into account, the cooling. And then cryptography plays a huge part in blockchain. So it's used to digitally sign transactions and that sort of thing. So I'm not going to go into cryptography, but I just want to explain that in some blocks, and also the makeup of blocks in different blockchains might be different. But let's just run through this example where you've got some data and you've got the hash of the preceding block. So I just want to demonstrate how these things are linked. So if, for example, you've got data, and doing a hash, really, you put some data through this hashing function, and you get this long bit of numbers and letters out. And what happens is, I'll just show it on here. So what you do to get that hash, it would have taken some data, the hash of the previous block, and then it produces this hash, which then in the next block is included as the hash of the previous block. So you see, that is one of the ways why it makes it so hard for malicious actors to change things, because they've basically got to go back and rewrite history. And that is what I wanted to demonstrate here. If you put some new data in there, then the hash, if you hash that new data with the preceding block, you're going to get something, oopsie, that is different. You're going to get a different number here, and so that's no longer going to correspond to the hash of the preceding block. And just for fun, I decided, well, I'll see what the hash of my name is, and the hash I get is that long thing there, and KCAC256 is a very popular hashing function. Now, the only change I did there is I changed from a capital letter to a lowercase s, and you can see the hash you get out is completely different. So it's just to demonstrate that that is the sort of thing that happens. Now, the types of blockchain you can have is, we talk about public and private blockchains, permissioned and permissionless. Now, with public means that everyone can see everything. Permissionless means that anyone can join that network. So a typical example would be Ethereum mainnet and the Bitcoin blockchain. They are permissionless and they're public. With a private network, typically it would be between parties who know each other. So you'd find that used a lot in, say, a financial institution might have a private network. And permissioned means only specific people can join that blockchain. And so you've got people looking at a combination of these things and creating blockchain solutions that would fit the requirements for the different use cases out there. So what's the conclusion of my talk then? Do we, in blockchain, we remove trust so that we can gain trust? Do you think that's true? False? Or it's a bit of both? I like to contend that the inherent need for us to trust necessitated the removal of trust. So if we kind of look at central versus distributed, that would be a trust thing. And even if, I was thinking as well, if you have like a dictatorship or something, versus a democracy, that would be decision-making is then in one place, or is it like coming to a consensus amongst a whole lot of other people? And the exciting thing is you can learn more. You can go and create your own blockchain network today. If you go to P1, P3 and P4 with my awesome colleagues over there, they're running the workshop today, and anyone can join, and I think it'll be a very exciting thing to do. And the other thing is, if you want to actually dig a little bit deeper into blockchain, tomorrow Sally is going to look at the anatomy of a blockchain, and that's at 1 o'clock tomorrow at P2, and I really encourage you to go along that, because Sally is going to look at what is a blockchain client, how does it work, and she'll then outline what are the key components of the blockchain as far as storage goes, mining, block propagation, and use cases for blockchain technology. So all the things I was not able to cover in a quick overview. So, and these are a lot of references if you really want to get into the sort of more technical side of trust in a trustless environment, or just trust per se. And I found myself, when I was preparing for this, I was wandering off all over the show, reading these really exciting, interesting references, and then I had to come back and say, no, I just wanted to communicate some key concepts. I'd like to acknowledge Grant. I pinched a couple of his slides, and two of my colleagues that I work with in the sidechains team, they gave me some constructive feedback, and my company for supporting our participation here at Hopper Down Under. And if there's time for questions, I think we've got about 1 minute for questions. Thanks, everyone.
blockchain is only a CR, which means you create and you read.
That's
you cannot
right.
update and you cannot delete. And
You-
what is your thoughts for the CR versus the CRUD for
Right.
the CR presenting a more trusted system because you actually have that historical record that can't be manipulated?
So, in my opinion, with a blockchain, what is good about it is you can trust the history because it's been verified, been validated by lots of people, not just one person, so you can't go back and change it. The only way you can change it is by adding an additional transaction to change it, so you keep that history. So it's a non-destructive way. There are other things that they're looking at, especially with private blockchains, where if you need to have a blockchain for just a short time, like, for example, deal negotiation, a particular deal, and this blockchain doesn't need to exist indefinitely, is there a way in which we can then archive it and then bring it back up when we need it, rather than having it running indefinitely? So that wouldn't be deleting it, but it would mean it's kind of archived to be brought back to life. But yes, the whole thing is that you don't want to delete or overwrite anything. So it's really like an audit trail. So I know when I was doing a lot of programming, a lot of things that we did, especially when we were updating things, is we'd create an audit trail, especially where you're trying to prevent fraud and that type of thing. Yeah.
And this one on the electricity, watching Netflix right now uses more electricity than the blockchain uses.
Really? That's a great bit of information.
But the blockchain is terrible for the environment. We should probably stop watching Netflix.
Thank you for that useful bit of information.
Hello, everybody. Whoa. Thanks, Jake. My name is Claudia. I'm from the University of Adelaide, and I'm your session chair for today. Now, you already know that we need to get out of the room. We need to exit the room once the presentation is finished. But anyway, we would exit because I believe there's lunch after this one. No pressure. So it is my pleasure to present Mahsa Salehi, who is from the Monash University and who's going to talk to us about driverless wearables and whether they can lead to more safer roads. Thank you, Mahsa.
Thanks, Claudia. Hi, everyone. Today I'm going to talk about how driver wearables can lead to safer roads. So first, a bit of introduction. I'm Mahsa Salehi. I'm from Faculty of IT, Monash University. My research is in machine learning and developing machine learning algorithms. This talk is an application of machine learning algorithms with collaboration with Dr. Fatema Jalali from IBM Research, Melbourne Lab in Australia. I did my postdoc in IBM Research where we were collaborating with Fatema. And we were both also, we did our PhD in University of Melbourne. Okay, wearables, Fitbits, most of us use Fitbits, so, or other physical activity monitoring systems, just like similar to these kind of physical activity monitoring devices. With recent advancements in brain-computer interface, we also have some other kinds of wearables that are for mind. So monitoring mental activities of human brain is what I'm going to talk about today. And when it comes to mind reading applications, you can think about many exciting, cool applications. So one of them that is very, very helpful is suppose that you have a wheelchair and you cannot actually move it, like for disabled people, they cannot move the wheelchair themselves with their hand even. So they can think, they can use their mind power to move the wheelchair forward or backward. So they can think about moving forward and then the wheelchair would move forward. Or they can think about turning right or turning left, and this would happen. So that would be very, very helpful and beneficial for disabled people. Another very, very exciting application that you can see on the right bottom side of the slide. So I used to play computer games a lot. I used to use wireless, actually, or even when I was a child, it was wired remote controls for playing computer games. So now imagine that you can actually think about moving avatars to jump or to move. So you would think about all of those and it would happen. So you play with your mind. Another application would be, which is on the right-hand side on the bottom, is actually piloting a drone with only the power of your mind. And, or even you can use it as actually these kind of wearable devices to actually, for architects or artists, they can use those kind of devices to see like which specific, what is your taste. Because, you know, emotions are something that you cannot quantify, and with using this kind of technology, you can do that. Okay, so lots of good and cool applications. Now this is one of the projects that I'm working on in collaboration with also Emotive, who is designing these kind of headsets that capture brain signals. So this specific project is about detecting driver distraction, and the partner company of Emotive, that they are from West Australia, and specifically they were interested to see if they can actually alert their truck drivers, because in West Australia the distances between cities is very long, and if you can actually monitor drivers not to get distracted, it would be very, very helpful for road safety. So that is a very important problem. And there are some statistics, of course, around like the main factor, one of the main factors in road accidents is driver inattention. And or 80% of collisions and 65% of near crashes have some sort of driver inattention as the contributing factor. So in the next few slides, I'm going to take you through all of the steps that we used to actually to identify driver distraction with using and monitoring brain waves. So first, the first step is data collection using cutting-edge wearable devices. The second step is data pre-processing and feature extraction. So we were interested in two important features or important characteristics of the brain waves, brain signals of drivers, to see which ones are useful and which ones are relevant to distraction patterns. And the third step is using artificial intelligence and machine learning models to identify those patterns, to learn actually those patterns, and develop models that can actually identify distraction for us. And the last step is model evaluation, and I will conclude this talk with a future potential of this project. Okay, for data collection, as I said, Emotive is a company that produces different wearable headsets that capture brain signals, and this is one of the headsets that's called Epoch, and these headsets are wireless. They are completely lightweight, and they can capture EEG signals with high rate. 128 hertz. In this headset has 14 different EEG sensors in it. So, and it can collect brain signals from different 14 locations on the brain. As well as these 14 sensors, there is also a gyroscope sensor at the back of the headset that actually captures head movements. And in these specific experiments, there are 18 participants, and each of them they were involved in a driving simulation for 40 minutes each. And so we actually imposed distraction to the drivers. For example, one of the distraction scenarios that we imposed was talking to them, or calling to their mobile phone, or ask them to send a text message. Another thing which was quite cool was that there were some arithmetic challenges on the road that we asked them to actually solve as they drive. And that would be like getting distracted by a billboard or advertisement or something else visually on the road. So these are the kinds of distractions that we actually imposed into this data set. And so these are the each of these. This one, for example, is an EEG signal coming from specific location on brain. And you can see that we have now 14 of these EEG signals. So after we collected data, this is the data pre-processing step where we bandpass filtered to remove noise from signals. Then we use the sliding window here and slide of size W to capture a subsequence of each of these signals over time, and we applied fast Fourier transform to transform these subsequences to their different bands. And that's because each of the mental states of brain, like distraction, focus, they are relevant to a specific band. So we extracted different bands, transformed these subsequences over time, and then we also extracted some specific features from those fast Fourier transform signals that are from on the sliding window. So for example, the peak or the distances between the minimum or maximum of the specific signal. So in other words, we actually could collect 200, so we extracted from those 14 signals, we extracted 266 features over time. So you can imagine that this is a very, in the context of machine learning, this is a high-dimensional time series data set. And it is very hard to detect and to do classification or clustering or other techniques. So on top of that 266 features that we had, we also add the gyroscope sensor that was on the back of the headset as well. Then we applied firstly a few existing machine learning techniques. So you might have heard about decision trees. This is a standard machine learning technique that's been used. And then we also looked into meta-learners. We looked into ensemble learning techniques, where two different techniques that we looked into is bagging and boosting. So in bagging, with any kind of base learner, which in this case we used random decision trees, we actually each model, this means that you have lots of decision trees, and each of them are trained over the data set separately, independently, and then we can, for purpose of prediction, we use all of these collection of decision trees to identify or detect whether that driver is distracted, for example, or not. So bagging techniques are used. The other technique, set of technique that we're using was boosting, where it refers to actually a group of algorithms, and in this case, decision trees, that utilize weighted average. So we use decision tree, and then for the observations that are not classified well or misclassified, we give higher weight to them, and we do this, and then we build a stronger model over some weak learners. So these two different algorithms, these two different techniques been used on this the data set that we have created. So we divided the data set. So we had 18 participants. So one option was to, like in machine learning, we always divide a data set into train and test. One option that we had was that we first divide, like we took all of the participants, the signals of those, brain signals of all those participants, and for example, used 2/3 of it to train the model and used 1/3 of it to test. But that would be an easy one comparing to dividing 18 participants like into two groups and train on some of the participants and test on the others, because the brain signals of each person might be different. So we thought, okay, we just challenge ourselves to divide the participants, like divide the tested and trained set based on participants. So we did that. We also used those annotations of distraction or non-distraction, because we have actually imposed distraction, and we had lots of those distraction scenarios that I talked about. We used those. So we knew that, for example, from time x to x plus 100, this specific driver has been distracted. So we annotated data set based on those distraction scenarios. And then used these two techniques, the random forest and the other boosting algorithm technique, to train model based on some participants and test on the others. And we used two sets of performance measures, AUC, area under curve of rock curve, which shows basically these two performance measures that we're using, the higher the better. So they're showing accuracy. The first one shows the relationship between false positive rate and true positive rate, and the other is for random forest and for the observations, using showing the accuracy of observations that are not being used in each tree in random forest. So these two are the performance measure that we've tested our algorithm on. These kind of results on the top side, they show, as I said, the higher the better. We wanted to see that because 266 features is a lot, so we thought, okay, can we reduce the number of features? And if yes, how far we can go? So using decision trees or random forest, we can do that. We can rank the features and see what are the best representative set of features that we can actually use. So 266, we used only the EEG, in this experiment we only used the EEG features and not the head movement feature, because we thought, okay, that might be easy to detect and make the algorithm to detect easier. We wanted to see if the model can actually, just only looking into brain signals, can the model detect distraction or not. And with 266 features, this is the OOB accuracy, one measure, and this is our second measure, and you can see that like we can get around 75, and then the other one is around 85% accuracy. And then we actually further down cut some of the features and looked into the most important features, 125 and 20 top best feature sets. And we found that, okay, the accuracy is dropping a bit because obviously we are losing some information, but we can see that it's kind of not that much we are losing. So we thought we stop here, because after this, even as we removed one of the features, it was all, the accuracy dropped a lot. We looked into the features that were here, and we found that these kind of features are the ones that are in related to the frontal lobe of the brain. And then these results are showing the EEG, like this graph is showing the results by EEG features only, and this is by EEG and also the head movement feature. And you can see that these features, the accuracy here is higher than the other ones. This sounds a bit of cheating to us, because if you're distracted, it seems that you're, turning your head a lot, or if you're text messaging, for example. But even without gyro features, we can see that's the highest accuracy. This is for random forest. This is with the boosting. And this is a very simple Gaussian mixture model that we actually thought to just test our model as well. These are ensemble learning techniques, and this is not an ensemble learning technique. So these needs more time consumption and memory consumption. But then we can have a higher accuracy. So the highest accuracy here, detection accuracy that we got is around 74%. Then we looked into more advanced AI models. We looked into, in the previous models, we actually looked into only each episode of time in the time series independently, for those of you who have been worked with decision trees, for example, or traditional machine learning. But in these sets of experiments, we looked into temporal relationships in the time series. So we were interested in to see what specific subsequence of patterns are showing a specific, a distraction pattern. And we found that the accuracy, and by developing these kind of algorithms, time series-based algorithms I can call, the accuracy increased. The accuracy by only looking into EEG increased to 81%, which was about 7% higher than the traditional machine learning. We also looked into so these are the results for just very, very recent. We also looked into deep neural nets and specifically CNN. And again, we looked into windows of observations, and again, using local information in the time series. And we also could even improve the accuracy to 90%. So we are quite very happy with the results of the algorithms that we've developed. So this is just an overview of what we've done. I didn't go through the details of specifically the two last algorithms, but I thought to just show the results. If you're interested, we can actually have a chat after the talk. For the future, I think this specific project has a very high potential. First of all, we can look into, actually Fatima and I, we are looking into implementation of of our model to hybrid edge and cloud computing. So whenever we have memory, we have time, capacity, then we can use more sophisticated models like deep neural nets. And when there's a limitation, then we can go back to a very simple, basic, traditional machine learning, and we can do this, we can learn this over time. This means that we can improve response time. You can imagine that how real time, it is very important that the responses to drivers, if we want to send alert to drivers in real time, it's very important to send that very fast. So other applications of this research, the other project that I was involved in, and this is an extension, the future potential is in safety. and how we can actually, in some industries, the risk of hazards or injuries, the risk of hazards and injuries by distraction, by getting distracted, is very high. For example, in construction companies, it's very, very important to be alert. And in those kind of environments, it is very useful for the workers, even because they're going to wear helmet anyway, to wear these kind of headsets to actually be more alert, to then decrease the, to increase safety. And so this is another project that I'm involved in. And the last one is also detection of other mental states, such as stress and emotion. So we only so far looked into distraction or level of focus of drivers. Okay, thanks so much. And I have another